These are the notes for AP Calculus on the topics of the ratio test and the root test. So both of these are two different tests to determine the convergence of an infinite series, whether it converges or diverges. So let's start with the ratio test. And this is if you have an infinite series and to determine if it converges or diverges, you find the limit as n approaches infinity of a sub n plus 1 divided by a sub n and absolute value of that, where that equals a limit between 0 and infinity. And then once you figure out what that limit is, if that limit is less than 1, then you know that the series converges. If the limit is greater than 1, then you know the series diverges. And if the limit equals 1, then the results are inconclusive using the ratio test. So then you would need to use a different test to determine whether the series converges or diverges. So let's take a look at this first example here. So what a sub n represents is the formula to find the nth term that's inside the series. It's right next to the sigma. So on this infinite series, let's use the ratio test. So we would find the limit as n approaches infinity of the absolute value of a sub n plus 1 means you would just substitute n plus 1 into our a sub n wherever there's an n. So that would be n plus 1 squared minus, there's another n there, so n plus 1 plus 2 divided by 2 to the n plus 1. And then that's divided by a sub n, just the formula as it is here. So that's n squared minus n plus 2 divided by 2 to the n. That's the absolute value of that. However, if you start looking at this, if you substitute in 1, you can see you get 1 minus 1 cancels out 2 over 2 to the first is 2, so that's positive 1. If you plug in 2, you 2 squared minus 2, which is 2 plus 2, and the denominator is always positive. So you can see you're never going to get negative numbers anyway, in which case you don't really need to worry about the absolute value. So you'd only do that at the very end if you ended up getting something negative. In this case, this is always positive. So to simplify this, well, remember when you divide two fractions, dividing by a fraction is the same as multiplying by its reciprocal. And we'll also simplify this one, the a sub n plus 1 by multiplying that out. So we'll do two things at the same time here. So if we square n plus 1, you get n squared plus 2n plus 1. Distribute the negative, gives you negative n minus 1, and then we have plus 2 over 2 to the n plus 1. And then instead of divided by that fraction, that's the same as multiplying by its reciprocal, which is 2 to the n divided by n squared minus n plus 2. So then it's just a matter of simplifying. So let's start by looking at the 2 to the n plus 1 and the 2 to the n. Well, all that means is this exponent on the denominator is 1 more than the exponent on the numerator. So an easy way to see that would be if you had some concrete numbers in there. If you had 2 to the third divided by 2 to the fourth, well, you would just subtract the exponents. You can see 3 of those would reduce out, so you'd end up with just 1, 2 on the denominator. So you're really just going 4 minus 3 to the first. And the same thing, you can see that how it would happen mathematically. If you took the exponent n plus 1 minus n, the n's would cancel, and you'd just be left with 1 for 2 to the first. So to reduce that, that's just going to be 2 to the first power. And at the same time, let's go ahead and simplify out this numerator here. So let's see what we have left. Remember, we're still finding the limit of this as n approaches infinity. So the going to n approaches infinity. We combine our like terms there, we've got n squared plus 2n minus n, usually plus n. And then the negative ones cancel, so then plus 2 divided by, got this 2 that was left over from reducing that. And then we've got, so actually you can distribute that out there. So if we distribute the 2 out to this, you can get 2n squared minus 2n plus 1. And then we have a normal limit that's easier to evaluate here. So on the numerator, when you substitute infinity, you can see infinity squared is going to outweigh the infinity and the 2, so we just have infinity squared over, on the denominator, the 2 infinity squared is what's going to matter most. And then the infinity squareds reduce out there, so you're just left with 1/2 is your limit as n approaches infinity. And since that's less than 1, that tells us that the series converges. Okay, let's look at another example with the ratio test. Slightly more complicated. And one of the types of problems that's oftentimes very good with a ratio test is when you have things with a factorial, with an exclamation point, which is called factorial. So let's go ahead and use the ratio test on this one, on this series. So use the limit as n approaches infinity of the absolute value of a sub n plus 1, means you substitute n plus 1 wherever there's an n. So that would be n plus 1 raised to the n plus 1 over n plus 1 factorial. And again, divided by a sub n plus 1. Sorry, a sub n as it is would just be n to the n over n factorial. So let's simplify this. So again, notice if you substitute 1, you get 1 to the first over 1 factorial, then 2 to the first, 2 to the second over 2 factorial. You can see you're never going to get any negatives here. So again, the absolute value doesn't affect this one, which oftentimes it doesn't. Occasionally it does. And then let's go ahead and simplify this. So we'll have n plus 1, the n plus 1 power, divided by n plus 1 factorial. And then that's times the reciprocal, and that would be n factorial over n to the n. Oops, get rid of it. So to simplify this, let's start with the factorials here. Notice factorial means like if it was 8 factorial, that, for instance, that would be 8 times 7 times 6 times 5, all the way down to 1. And notice this is a 1 more factorial. So if that was 9 factorial, for instance, 9 factorial would be 9 times 8 times 7 times 6, 5, all the way again down to 1. So you can see that would reduce, in this case, when these are divided by each other, 8 through 1 would reduce out to just be 1, and all you'd be left with is that 9 other number, which in this case is n plus 1. So we could reduce that out, and all that would be left would be just n plus 1, so whatever that number is. And then once we have that, you notice we'll have n plus 1 to the n plus 1 divided by n plus 1. So this is like n plus 1 to the first power. And again, like we saw in the other one, you would just subtract the exponents. For instance, if you had, let's say, 3 to the 5th divided by 3 to the 4th, you would subtract the exponents. 5 minus 4 would give you 1. Be 3 to the first. In that same fashion, if we take the exponent n plus 1 minus this exponent 1, you can see the 1's cancel out and you're just left with n. So we have n plus 1 to the nth power, and then this divided by n to the n. And since they're both raised to the nth power, you could write it like this. This one over n, the whole thing. Oops, sorry, I put a square there accidentally. That was to the nth power. The whole thing to the nth power. And then to figure this out here, you can split this up. N divided by n is 1 plus 1 divided by n to the nth power. And then we have the limit as n approaches infinity. So when you first see this, if you substitute infinity, you might think, well, infinity going there would make this approach 0, and then you just have 1 to the infinity, which would be infinity. But that would give you the wrong answer. And if you think about it, you can see why that would be, because if you have 1 plus something more, right, you keep multiplying by things that are a little bit more than 1, those get bigger than 1. Those are actually get closer and closer to 1. So this isn't going to be 1. And this is actually one of the famous limits in calculus. To see what it equals, let me show you on using a graphing calculator how we can figure that out. So you can see I've entered in the function. I just put in x there instead of n. And you can see as x approaches infinity, or in our case n approaches infinity, it does approach some value. Notice it's not even close to 1. That's up here. Looks like it's closer to 3. To see exactly what it approaches, let's go ahead and substitute in some numbers into that. Some big number. Let's say we plug in 100 for n. Okay, we get 2.704. What if we plug in 1,000? What if we plug in 10,000? So you can see the value we're getting closer and closer to right there is actually E. So that's what this limit equals. It's E. So that's in one of the famous definitions of E, one of the famous limits in calculus, that it just approaches E there. And since in our case we're looking to see whether this is greater than or less than 1, in this case that's greater than 1, so that tells us that this series diverges. Okay, now let's take a look at the root test. The root test works in a very similar fashion to the ratio test, except it says if the limit as n approaches infinity of the nth root of a sub n equals some limit, where the limits between 0 and infinity. If that limit is less than 1, then you know the series converges. If the limit is greater than 1, then the series diverges. And again, if it equals 1, the results are inconclusive using the root test. So basically the same thing on this part as the ratio test. So it says use the root test to determine whether infinite series converges, diverges, or if the results are inconclusive. So to figure out if this series diverges or converges, again, the ones where the root test tends to work well is when you have like the whole thing or part of the numerator denominator raised to the nth power, like this one. So if we use the root test and find the limit as n approaches infinity of the nth root of 4n minus 3 over 2n plus 1 to the nth, you can see the nth root and the nth exponent would be inverses of each other, so they would cancel out. So all you'd be left with here is a normal limit problem. The limit as n approaches infinity of, all that's left is 4n minus 3 over 2n plus 1. And now if you substitute infinity, you can see, well, the negative 3 is going to be negligible in the numerator, so that would be 4 times infinity over the plus 1 is going to be negligible on the denominator, 2 times infinity. The infinities would reduce that, leaving you with 4 divided by 2, which is 2. And since that's greater than 1, that tells us this series diverges using the root test. And let's take a look at one more example using the root test. On this one, again, we can see it might be helpful because the denominator is raised to the nth power. So it would be a limit as n approaches infinity of the nth root of 1 over the natural log of n plus 1 to the n. So then let me take the nth root of the numerator and denominator separately. The nth root of 1 is just 1 over the nth root of the natural log of n plus 1 to the n. They're the nth root of the n exponent are inverses, so they cancel out. So you're just left with the natural log of n plus 1. And then if you substitute infinity, you have 1 over the natural log. Plus 1 is really negligible, so the natural log of infinity. And the natural log of infinity, well, infinity, our natural log graph, looks roughly like this. So it does keep going up and up forever, even though it's kind of slow right there. So since that denominator gets bigger and bigger, and the numerator is just 1, you can see the denominator gets so big that this is approaching 0. And since 0 is less than 1, that tells us that this series converges. And that concludes the notes for AP Calculus on the topics of the ratio test and the root test.